Hello everyone, welcome to the online lecture on Applied Electromagnetic Theory. Myself, Shyama Srikumar, Assistant Professor, Department of ECE, Rajagiri School of Engineering and Technology. Today I'll be continuing with the lecture on Module 4, which is about transmission lines. In the previous lecture, we discussed about the basics of transmission line equivalent circuit, transmission line parameters, and the solution to transmission line equations. Now, we'll be studying about the parameter, characteristic, impedance, and two special types of transmission line called as lossless and distortionless transmission line. So one of the parameters used to characterize a transmission line is called as characteristic impedance, and it is denoted by Z0, and it is defined as the ratio of the positive traveling voltage wave to the amplitude of positively traveling current wave at any point on the line. So you already know impedance means it is voltage by current. Characteristic impedance is a property of transmission line which takes the ratio of positive traveling voltage to positive traveling current. And this is similar to the term intrinsic impedance which we derived in the case of electromagnetic wave propagation over free space or unbounded media. So when you consider the expression for Z0, to derive that, we are making use of the expression for voltage, which is Vs of Z. And it was V0 plus e raised to minus gamma Z plus V0 minus e raised to gamma Z. And we are going to substitute it into the first order differential equation given by minus dVs by dz equal to R plus j omega L into Is. So when you take the first derivative of Vs with respect to Z, we will get it as this form. So e raised to minus gamma z, derivative is minus gamma, e raised to minus gamma z, e raised to plus gamma z has the derivative gamma into e raised to gamma z. And this is also replaced by the solution which is I0 plus e raised to minus gamma z plus I0 minus e raised to gamma z. Now, to determine the ratio of V0 plus by I0 plus, I am going to equate the coefficients for e raised to minus gamma z. So, when you observe the LHS, the coefficient is gamma V0 plus. When I observe the RHS, the coefficient is R plus j omega L into I0 plus. Similarly, if we equate the coefficients for e raised to gamma z, on LHS the coefficient is minus gamma V0 minus, and on RHS it is R plus j omega L into I0 minus. From these two equations, from the equation A, if I take V0 plus by I0 plus, it is R plus j omega L by gamma. Similarly, when you take it from this equation, minus V0 minus by I0 minus is again R plus j omega L by gamma. This R plus j omega L by gamma is what is called as the characteristic impedance. So characteristic impedance is given by the ratio V0 plus by I0 plus, or it is given by the ratio minus V0 minus by I0 minus. So from this expression, we'll get the value of characteristic impedance as R plus j omega L by gamma. And what is gamma? It is called as the propagation constant, which is given by root of R plus j omega L into G plus j omega C. On cancelling one root of R plus j omega L, we will get the expression for characteristic impedance Z0 as root of R plus j omega L by G plus j omega C, which is called as the characteristic impedance, and it is measured in ohms. So this Z0 can also be expressed as the ratio of impedance, which is the series impedance of the series elements R and L divided by the shunt admittance Y. So Z0 can be written as root of Z by Y. So now we'll see two special types of transmission lines. One is lossless transmission line and one is called as the distortionless transmission line. So when you consider a lossless transmission line, the conductors and the medium should be perfect and it should be lossless. So if you consider the conductor, if it is a perfect conductor, then the conductivity will be very high. So this conductivity will be approximately infinity. So if conductivity is infinity, the resistivity will be zero, since conductivity is inversely proportional to resistivity. And when resistivity is zero, the value of resistance will be zero, since the expression for resistivity is rho equal to Ra by L. So one of the conditions for a lossless transmission line is that for this conductor to be perfect, the series resistance should be equal to 0. And the second condition is confining to the dielectric medium present. So when you consider the dielectric medium, it is not a conducting medium. If a dielectric medium has to be perfect, the conductivity should be 0. If conductivity is 0, the value of resistivity will be infinity, which makes the value of resistance to be infinity since rho equal to Ra by L. When you consider the medium, the element which we use is the conductance G. So when you consider conductance, it is a reciprocal of resistance. So the value of conductance will be equal to 0. So the essential condition for a lossless transmission line is that the value of resistance and conductance will be equal to 0. That is R equal to 0, which is equal to G. Thus, a transmission line is said to be lossless if the conductors are perfect, that is sigma C will be infinity, and the dielectric medium separating them will be lossless, that is the conductivity of the dielectric medium will be equal to 0. So we have derived the condition for lossless transmission line as R equal to 0, which is equal to G. So we'll derive the expression for characteristic impedance and propagation constant in the case of a lossless transmission line. So when you consider the propagation constant, the expression is gamma is equal to root of R plus j omega L into G plus j omega C. So when you consider this expression, the value of R and G is 0. So what will happen? Gamma will become root of j omega L into j omega C. When you take the square root, it will be equal gamma equal to j omega root of LC. And the unit of propagation constant gamma is meter inverse. So as you all know, gamma is having real part which is alpha and imaginary part is beta. Since it doesn't have any real part, the value of attenuation constant is 0 Nm per meter. When you consider this is the imaginary part, so the value of phase constant which is beta, it is equal to omega root LC. And the attenuation constant 0, and this implies that the transmission line is lossless since it is not suffering any losses while the signal is transmitted from generator to the load. And the value of phase constant we got, it is in radians per meter. When you consider the expression for characteristic impedance, it is given by root of R plus j omega L by G plus j omega C. When you substitute the condition R equal to 0, which is equal to G, we will get root of j omega L by j omega C, and that is equal to root of L by C ohms. This is the value of characteristic impedance of a lossless transmission line. Now, when you consider the velocity, the expression is U is equal to omega by beta. Already we know beta equal to omega root LC, so we'll get the velocity as 1 by root LC, and the unit of velocity is radians per second. So if in our case of solving the problems, if it is given as lossless, we can substitute these expressions and find the value of beta, Z0 and velocity. So the next type of transmission line is called as distortionless transmission line. So when you consider any signal which is transmitted, it is made up of a band of frequencies, or it is any periodic signal can be expressed as a sum of frequencies or sum of harmonics. So when you consider each signal, if the attenuation is dependent on frequency, what will happen is that each wave frequency will get attenuated by different amounts since the attenuation is dependent on frequency. So if the medium is lossy, then the attenuation constant will be dependent on frequency. So what will happen is that each frequency component will experience different amounts of attenuation. So hence the signals will suffer distortion while transmitting from source to the generator. So a distortionless transmission line is the one in which the attenuation constant should be independent of frequency. That is, it should be a constant value. Whatever be the frequency, the attenuation should remain constant, and the phase constant is a parameter which is linearly dependent on frequency. And the condition for a distortionless transmission line is given by R by L is equal to G by C. condition for distortionless transmission line was given by R by L equal to G by C. So when you consider the propagation constant gamma, it is root of R plus j omega L into G plus j omega C. So to incorporate the condition R by L equal to G by C, we are taking a R outside from the first term and G outside from the second term. So the expression reduces to root of Rg into 1 plus j omega L by R into 1 plus j omega C by G. So when you consider these two terms, in this L by R is equal to C by G from the condition for distortionless line. So what will happen to the value of gamma is that gamma will become root of Rg into 1 plus j omega L by R, since these two terms are equal. So when you open the bracket, value of gamma will be root Rg plus j omega L into root of G by R. Now when you consider G by R, it is equal to C by L from the condition. So when you substitute it back, it is j omega L into root of C by L. Hence we will get gamma is equal to root Rg plus j omega root Lc, which is measured in meter inverse, and it is called as the propagation constant. So when you separate the real part, it is the attenuation constant alpha, which is equal to root Rg. So when you consider alpha, it is in Nabla per meter, the value is constant, that is, it is independent of frequency. So we can tell that the transmission line is said to be distortionless. When you consider the phase constant beta, it is measured as omega into root of Lc from the imaginary part of gamma, and it is measured in radian per meter. As expected, the phase constant is dependent on frequency. To derive the expression for characteristic impedance, it was Z0 equal to root of R plus j omega L by G plus j omega C. So to apply the condition R by L equal to G by C, similarly we are taking R outside from the numerator and G outside from the denominator. So the expression reduces to root of R by G into 1 plus j omega L by R into 1 by 1 plus j omega C by G. So when you consider these two terms, both remains equal since R by L equal to G by C. So the value of Z0 reduces to root of R by G, and this R by G is again equal to L by C. So Z0 can also be expressed as root of L by C ohms. So the expression for characteristic impedance in the case of a distortionless transmission line is given by Z0 equal to root R by G, which is equal to root of L by C. And when you consider the velocity, it is again omega by beta, and you will get the same value, which is 1 by root LC radians per second. So the velocity remains the same whether it is a lossless transmission line or a distortionless transmission line. So we got the values of alpha, beta, Z0 and U in the case of distortionless transmission line. That is, we got alpha equal to root Rg, beta is equal to omega root Lc, and Z0 can be expressed as root of R by G or root of L by C, and velocity was equal to 1 by root Lc. So we can get the values of RL, G, C, that are the primary constants of a transmission line, from the values like alpha, beta, Z0 and U. So when you consider the expression for alpha, when we multiply it with Z0, we will get what is called as the resistance per unit length R. So R can be found as R equal to alpha Z0. When you divide alpha by Z0, you will get the value of G, which is the conductance per unit length of the shunt arm. And again, when you consider velocity and the Z0 characteristic impedance, you will get the value of inductance as L equal to Z0 by U. And when you consider the capacitance C, it will be equal to 1 by U Z0, where U is the velocity and Z0 is the characteristic impedance. So these expressions can be used to determine the transmission line parameters using the given values of Z0, alpha, beta and the velocity. So when you compare a lossless line and a distortionless line, when you consider a lossless line, it is always a distortionless line as well, since R equal to 0 equal to G is satisfied even if R by L equal to G by C. But when you consider the condition for distortionless line, R and G need not be 0 always. So the converse is not true, that is, a distortionless line need not be lossless always. So when we consider both the scenarios, a lossless line is mainly used for power transfer so that we'll get the maximum power at the output load. When you consider distortionless line, it is used in telephone lines for private transmission of information. So this is the comparison between lossless and distortionless line, and the parameters are the expressions which are in the case of lossless and distortionless lines. So here we have just consolidated all the expressions which we have learned till now. First one was the propagation constant, then we derived wavelength velocity, then we got the expression for characteristic impedance, and we studied two special types of transmission line. One is the lossless transmission line where we got alpha is equal to 0, and the second one was distortionless transmission line by applying the condition R by L equal to G by C. And then we determine the four primary constants of the transmission line in terms of alpha, Z0 and velocity. So now we'll try to solve some problems using these equations. So we'll consider a problem where we are having an air line which has a characteristic impedance of 70 ohms and a phase constant of 3 radians per meter at a frequency of 100 megahertz. We are asked to calculate the inductance and capacitance per meter length or unit length. So it is C and L we should determine. So when you consider an air line, the medium is air. So this can be considered as a lossless transmission line. So in the case of lossless transmission line, the expression for characteristic impedance is Z0 equal to root of L by C, and the phase constant beta is given by omega root LC. So this root L by C is equal to 70 and omega root LC is equal to 3. So when you consider omega, it is 2 pi f, where f is 100 megahertz. So when you substitute that value, it is 3 by 2 pi into 100 into 10 raised to 6. So we'll get the value of root LC as 4.77 into 10 raised to minus 7. So when you consider these two equations, one is root of L by C and the other one is root LC. So when you multiply the two equations 1 and 2, you will get the value of L and you will get the value of inductance as the value of inductance you will get it is 70 into 4.77 into 10 raised to minus 9. So the value you will get is 333.9 nano henry per meter. And when you divide equation 2 by 1, you will get the value of capacitance, which is 4.77 into 10 raised to minus 9 by 70. And hence the value of capacitance we obtain is 68.14 picofarad per meter. Hence we have determined the value of L and C using the expression for characteristic impedance and phase constant. So now we'll consider a problem with the help of distortionless transmission line. So we are having a distortionless transmission line with characteristic impedance 60 ohm, attenuation constant 20 millinever per meter and velocity is 0.6 c, where c is the velocity of light in free space. So we are asked to determine the primary constants of the transmission line and the wavelength at 100 megahertz. So with the given values, we can determine R, L, G, C using the expressions R equal to alpha Z0, G equal to alpha by Z0, L equal to Z0 by U and C equal to 1 by U Z0. So when you substitute the values of alpha and Z0 into R and G, we will get R as 1.2 ohms per meter and the value of G we will get it as 333.33 microsiemens per meter. So all the resistance, conductance, etc. measured per unit length. So we should write the unit as ohm per meter, siemens per meter, etc. Now when you consider Z0 by U, we should substitute characteristic impedance and velocity. So we'll get the value of inductance L as 333.33 nano henry per meter. And the value of capacitance C is 1 by U Z0. So you will get it as 92.59 picofarad per meter. Now when you consider, we need to determine wavelength at 100 megahertz. So when you consider the expression for wavelength, we know velocity is equal to frequency into wavelength. We already know velocity as well as the frequency. So we can determine the wavelength as U by F. So we will get it as 1.8 meters. So this problem is using the concept of distortionless transmission line to determine the four primary constants of transmission line, that is R, L, G and C. So we'll conclude this lecture on transmission lines. In this lecture, we learned about characteristic impedance, the expression for characteristic impedance. Then we learned two special types of transmission line. One is a lossless transmission line and the other one was distortionless transmission line. And we make use of the concepts of lossless and distortionless to solve the problems with respect to transmission lines. Thank you.